Cisco iOS provides 3 sets of tools for frame relay traffic shaping. These techniques are often referred to as GTS, FRTS, and class-based. This presentation focuses on the fundamentals of FRTS. We cover class-based shaping and shaping for voice QoS in later presentations. Most frame relay networks will implement frame relay traffic shaping to meet one or more of the goals you see here. Mismatched access rates can lead to very poor network performance over frame relay. For example, if a headquarters site has a T3 connection to the frame cloud, it may attempt to send traffic up to 44 megabits per second over any given PVC. If a branch router on the other end of that PVC has only a T1 access rate, then most of that traffic is going to be dropped. This condition is called egress blocking. We will see how FRTS can help us here. Alternatively, it may happen that both routers have the same T3 access rate, but the PVC between them is only T1. If the ISP is strictly enforcing the PVC rate, then it will drop the excess. FRTS can also help us here. By default, only physical interfaces have manageable queues. Subinterfaces and DELCs must share it. FRTS creates a 40-packet queue per PVC, which can be managed to guarantee bandwidth and create a priority queue. FRTS also enables advanced fragmentation features that can help reduce delay and jitter. As we will see in a later presentation, these features of FRTS are critical to supporting voice over IP traffic over frame relay. The effectiveness of traffic shaping relies on the fact that most network traffic is bursty. The rate of traffic on an interface is usually not constant, but varies around the mean value. Traffic shaping is an attempt to save traffic in a buffer during the peaks and then send it when the rate is low. There are important practical limits to this technique. One is the size of the buffer. Each stored packet requires RAM, and RAM is a limited resource. A related problem is that of acceptable delay. While these packets are being stored on the sending router, an application at the destination is waiting for them. Some applications are more sensitive than others to delay. FTP can tolerate a lot more delay than can voice over IP. Buffering can also lead to jitter, which is variability in delay. The 3 methods of shaping traffic over frame relay links offer various strengths and weaknesses. Generic traffic shaping uses the traffic shape command on the interface. One advantage of GTS is its ability to shape a subset of traffic defined in an access list. Another advantage is its relative simplicity. FRTS requires that we enter the command frame relay traffic shaping on the physical interface. It has been widely used for many years and has a fragmentation technique, FRF12, that is useful for voice over IP. On the downside, FRTS shapes all traffic on all DELCs with default parameters. As we'll see, default shaping values are changed by creating a map class and applying it to individual PVCs. Class-based shaping is the newest of these tool sets. It can be applied at the interface, subinterface, and PVC level. Class-based shaping allows us to shape complex subsets of traffic in powerful ways. Let's see how we can use a simple FRTS configuration to save us from an access rate mismatch problem. The hub router, R1 in our scenario, is configured with a T3 link to the provider, and the remote office, R2, is connected by just a T1. Users are complaining of poor network performance, yet average utilization of the T1 is reasonable. The problem may be that large bursts of traffic are being sent by the hub and dropped by the provider switch connected to the T1. To address this, we will try to shape the traffic coming out of the hub router to T1, a rate the branch link can handle. Here is how we create and apply it on R1. First, we create a map class frame relay in global configuration mode. Here we set the CIR to T1, our target rate. We will try to buffer any traffic over this rate and send it when the peak subsides. Next, we must activate frame relay traffic shaping on the physical interface. Finally, we go into the subinterface and apply the map class to the ccnp using the class command. We use the command showTrafficShape to give us a quick view of the shaping parameters. Note PVC102 has our target rate. The byte limit and interval are critical features of FRTS. The physical interface can only send traffic at one rate, T3 in our example. To get the interface to send at a T1 rate, FRTS doles out the traffic to the interface at the rate of 6,144 bytes every 32 milliseconds. If PVC102 traffic is the only traffic on the interface, then it will send 6144 bytes at a T3 rate, then wait until the next 32 millisecond interval and send another 6144 bytes. This will happen 32 times until the interface has sent a total of 1,536,000 bits, or 192,000 bytes, in 1 second. The byte limit and interval are calculated automatically by the router based on the CIR. The table you see here gives these values for some other rates. Note, by the way, that PVC103 is being shaped to a rate of 56K. Forgetting that FRTS applies this rate to all PVCs by default could be a career-limiting move. Let's create a map class that demonstrates some of the power of FRTS. Imagine the same hub and remote offices, but now we have only a 384K PVC between them. As long as the network is not busy, our provider lets us send up to 512K. When the provider network does get congested, it marks traffic over the PVC rate as discard eligible and signals us to throttle back by having the beckon bit set in return traffic. In the past, we found that we can usually get away with sending at a T1 rate for short periods. In addition, we want to send traffic to the interface every 10 milliseconds instead of every 125. Here is the map class that will implement these policies. The interval at which bytes are sent to the interface has an effect on delay and jitter. Though the iOS syntax options appear to allow TC to be set directly, it doesn't actually work. To set TC, you set committed burst, or BC. The fraction of BC over CIR results in TC. Note that the excess burst value, BE, is the difference in bits per second between our CIR and our peak rate of 1,536,000. The excess burst value comes into play when we have been sending below CIR for a time. Every byte that we could have sent but did not is credited to excess burst. The min CIR value is our PVC. Because we have enabled adaptive shaping based on beckons, our router will reduce its sending rate when the provider is congested. We have paid for a guaranteed PVC of 384K. The min CIR sets a floor below which we will not throttle. Next, we'll apply our map class to ccnp-ccie and observe the result. Note the sustained bits per interval is 5,120 bits, or 640 bytes. This is our committed burst. Our byte limit is 128,640. This is the 640 bytes from the sustained rate, plus 128,000 bytes of excess burst. Note that we are not actually permitted to send this byte limit every 10 millisecond interval. The excess burst is spread over the interval of 1 full second, so the byte limit figure is not very meaningful when excess burst is configured. There are 4 map class options related to FRTS on DTE interfaces that we have yet to mention. They are FECN-ADAPT, Hold Queue, TC, and Traffic Rate. FECN stands for Forward Explicit Congestion Notification. This feature works with BECN, Backward Explicit Congestion Notification, to get senders to throttle back during congestion. When frame relay switches are congested, they can set the BECN bit in the Q922 header. When the FECN-ADAPT is configured on the receiving router, it can set the FECN bit in the header in frames destined back to the sending router. If the sending router has adaptive shaping BECN configured, it will throttle its sending rate back. The Hold Queue map class command controls the size of the shaping buffer. It is 40 packets deep by default. It can be configured between 1 byte and 1024. The presence of the TC command in map class configuration mode suggests that the shaping interval can be set directly. This is not the case. The documentation says it should be used to set the TC when the CIR is 0, but we have not yet seen this work. For data traffic, it is best to let the router scale TC automatically based on CIR. If you need to set TC, it must be done indirectly by setting the committed burst. The traffic rate command is an alternate syntax for setting the CIR and the excess burst. In our earlier example, we set CIR to 512K and the maximum rate to T1, or 1536K. There, we set the BE value to 1024K, the difference between 1536 and 512. The traffic rate syntax allows us to set CIR and EIR, excess information rate. EIR is the peak rate. Here is how it would be configured in iOS. The traffic rate command simplifies the excess burst calculation, but it is not well documented. It does not permit the specification of TC, and we do not recommend it at this time. In order to demonstrate traffic shaping, we have a traffic generator sending a stream of UDP packets to R1 and then across the frame relay connection to the loopback on R2. This stream averages 64 kilobits per second, but it varies randomly between about 56K and 72K. To simulate an access rate mismatch, we have configured the clock rate on FRS port S1 to 64K. This is the output port for traffic from R1 to R2. We have changed the port buffer size to 5 packets from the default 64 packets. First, let's see what's happening on port S1 of FRS. Note that there are currently no packets in the queue, but since the last clearing of the interface counters, a total of 145 packets have been dropped because the 5-packet buffer has overflowed. Let's take another look at this interface. We'll simply repeat the show command. Up now we've dropped 183 packets. 183. Up to 190, and right now we see that there are 4 packets currently in the 5-packet buffer. Since our traffic average is 64K and the clock rate is 64K, we may be able to keep the frame relay switch from buffering and dropping packets by implementing frame relay traffic shaping R1.